Hello everybody. In this video I'm going to go over the problem that we did in class today. In that problem we had two initial concentrations for the reactants and an equilibrium constant. And the question asked us to determine the equilibrium concentrations for both reactants and the product, right? So let's go ahead and take a look at the problem. So the first thing to note is that we have a 1 liter flask. And in this 1 liter flask we have 1 mole of hydrogen gas and 2 moles of iodine gas. That's helpful because it tells us what the concentration of each gas is in the flask, right? So for hydrogen gas, it's going to be 1.0 molar for hydrogen gas. And then for iodine gas, 2.0 molar. And then now the only other piece of information in this question that's helpful to us is that the equilibrium constant, or Kc, is equal to 50.5, right? We don't need the temperatures for this particular problem, right? Because the problem is only asking for the equilibrium concentration for the hydrogen gas, the iodine gas, and then the hydrogen iodide gas, right? So temperature is not required for that, right? Not required for that. So what's the first step in doing any equilibrium equation problem or any equilibrium problem? It is to have a balanced chemical equation, right? So our balanced chemical equation is H2 plus I2 becomes HI. Now, is this equation balanced yet? No, it's not, because we have 2 hydrogens and 2 iodines on the left side and only 1 of each on the right side. So this is easily remedied by just putting a 2 in front of the HI, and now we have 2 of each on both sides. Okay. And then after that, the next step of doing any of these equilibrium problems is to draw an ice table. And I'll draw the ice table right under the balanced chemical equation so that I can make my columns line up with each of the components of the reaction, the two reactants and then the product. Right? And of course, you're going to have 3 rows because it is an ice table where I stands for initial, C stands for change, and then E stands for equilibrium, right? Or concentration at equilibrium. And so from our problem, we can fill in part of the ice table, right? We can fill in part of the ice table. So just imagine that this is like the concentration. This column will be the concentration of H2. This column will be the concentration of I2. And then this concentration here, or this column here, will be the concentration of HI, right? So we can fill in the gaps we can fill in the boxes on the top row from the problem, right? So here's the 1.0 molar for H2. 1.0 molar, right, for H2. 2.0 molar for I2. For I2, both of those are initial concentrations for those reactants. And then, what is the initial concentration for the product, HI? Well, at this point, the reaction hasn't started yet, so the initial concentration is 0, right? The next the next row is change, right? And the change, like we discussed in previous examples, really represents the loss of reactants during the course of the reaction to get to equilibrium, and the gain of products, right, during the course of the reaction to get to equilibrium. And so, in that thinking in that way, we know that as the reaction progresses, we will lose some amount of each reactant. That's represented by a minus sign, right? And then we will gain some products, and that's represented by a plus sign. But we still have to be able to figure out a number there, right? Some kind of value. And that value we'll use x to represent. So, for example, then, or I'll just write up here, loss of reactant can be represented with value. That value can be represented with an x, right? So, in the ice table, we lose x, of H2 during the reaction. We lose X as well for I2 in the reaction towards equilibrium. But we gain X, right, for the product. Is it just X, though? No, it's not just X, because remember, we have a 2 here for the coefficient. So it's not just X, it's actually 2X. This is great, because now we have the second row filled out. So how do we fill out the third row? Well, the third row is even easier, right? Because we don't have to do any thinking here, right? It's just regular, arithmetic. Because to get the equilibrium concentration for any of the reactants, it's just the initial minus the change, right? And then for the product, it's the initial plus the change. And so let's do that. Initial, which is 1.0 for hydrogen, minus the change, which is X. And then for iodine, 2.0 minus X for the equilibrium concentration. And then for the product, which is hydrogen iodide, it's 0, which was the initial, plus 2X. That's great, because now we have the entire ice table filled out. You might be asking yourself, we still don't have any values, right? What are we going to do? Well, that's where the Kc comes in, right? That's where the Kc comes in. So the Kc, or the equilibrium constant in this case, right? Recall is Kc equals the concentration of hydrogen iodide, right? And it's not just hydrogen iodide, but it's hydrogen iodide squared. Why is it squared? It's squared, again, because of this coefficient right here, the 2 coefficient. All that is divided by the concentration of H2 times the concentration of I2, right? And the great part about this is that we actually have equations or terms from the ice table that we can plug in to fill in the gaps for, or fill in the concentrations for HI, for H2, and I2, right? So let's go ahead and do that. So for HI, what we're going to have is this down here, right? At equilibrium, it's 2x. But again, it's not just 2x. It's 2x squared because of the exponent. So don't forget to do that. I always put my 2x's into parentheses with an exponent to make sure that the calculator knows that both the 2 and the x are getting squared, not just the x, right? And then down here below the line, it's going to be the equilibrium terms for H2 and I2, right? So for H2, it's going to be 1.0 minus x times the term for I2, which is 2.0 minus x. And then all this, again, is equal to what? The equilibrium constant. So 50.5. That's great, because now we have an equation that we can solve for x. And x represents our loss, and that loss in x can be plugged in here, here, and here to solve for the equilibrium equation. Equilibrium concentrations for each of the reactants and the product, right? So what we just did here is what I would refer to as the chemistry part, okay? So all this stuff right here that we just did, right? All this, I would refer to this as the chemistry part of the problem. Okay, the chemistry part of the problem. And the reason why I say that is because the next part of the problem will be the math part, where we actually go through and solve for x in this equation right here. Okay? And if you notice, this equation has an x squared term, it has an x term, and it also just has a number, right? Wow, that sure does look like the requirements for a quadratic equation, right? Or using the quadratic formula, okay? But recall, though, that the quadratic formula requires that we have 0 equals ax squared plus bx plus cx, right? And while we have all those terms available in our equilibrium expression, they're not in the form that's required for the quadratic equation. Because recall that the quadratic equation is x equals minus b, right, plus or minus the square root of b squared minus 4ac, all divided by 2a. So you can see how now we've moved into the math part, right? So everything below this line here is the math part, right? It's the math part because we have to go through and solve for x using the quadratic equation, which is, I don't know how much more math you can get, all right? But for us, again, to use the quadratic equation, we have to rearrange the equilibrium expression into this form right here, the ax squared plus bx plus c, right? So how am I going to do that? How am I going to do that? Well, I'm going to go ahead and move to the next page so that I have a little bit more room to do this, okay? And so I'll rewrite everything again. We started out with 2x squared, right? I'm going to erase that and fix that so that I have a little bit more room. I'll squish those two in a little bit too close to each other. So we start out with 2x parentheses squared. All that is over 1.0 minus x times 2.0 minus x. And all of that is equal to 50.5. Okay? That's what we had from the previous slide, previous page. Okay? So what is the first step in rearranging everything, right, in this expression so it's in the form of 0 equals ax squared plus bx plus c, so that we can use the quadratic equation, which is x equals minus b plus or minus the square root of 4 squared, my apologies, got ahead of myself, I meant b squared minus 4ac all over 2a, right? So what's the first step? What is the first step? Well, the first step is to, I would think, or I would do, is I would FOIL the bottom term. What I mean by that is multiply the 1 to the 2, and then the 1 to the minus x in the second term. And then I would do that again with the minus x to the 2, and the minus x to the other minus x, right? So this step is called FOILing, and that's what I would do as my first step to getting the expression, the equilibrium expression, to look like that form right there, right? The quadratic form. So when I do that, what I'm going to end up with is x squared minus 1x minus 2x plus 2, okay? And just to be clear about where that comes from, right? We have the minus x times the minus x gives us x squared, right? And then we get the 1x times the minus x gives us the minus 1x. And then we have the minus x times the 2 gives us the minus 2x. And then the 1 times 2 gets us the 2. So that's where that comes from, right? So I'm going to go ahead and simplify all this down now. The numerator and the denominator, right? I'll go ahead and square the 2 and the x in the denominator, in the numerator, and then combine like terms in the denominator. And so what I will end up with is 4x squared, all of that divided by x squared minus 3x plus 2. And then all of this is still equal to 50.5. Okay, 50.5. Okay, great. It's starting to look more and more like the quadratic form that we need. What else do we need to do? What else? What's the next step, right? Well, I don't like having a denominator or a fraction, right? So I'm going to have to try to get rid of the fraction. How do I do that? I'm going to multiply both sides by the denominator. So that's x squared minus 3x plus 2 times the left side. And then the same thing for the right side. X squared minus 3x plus 2. Well, on the left side, that's easy because we have a x squared minus 3x plus 2 in the up there, multiplying towards the denominator, so they both cancel out, right? Multiplying to the denominator, they both cancel out. And then on the right side, we will go ahead and distribute the 50.5 to the x squared, then to the negative 3x, and then to the 2, right? That gets us to this point here, where we now have 4x squared equals 50.5 times x squared is 50.5 x squared, okay? And then 50.5 times negative 3x gives us minus 151.5x. And then 50.5 times 2 gets us a nice 101.0. All right. It's looking a lot more like the quadratic form that we need for the quadratic formula, right? Very, very much so. So how do we get it there? There's one more step now, right? One more step and we'll get it to the correct form. And that step is getting this 4x squared to become a 0. How do we do that? Subtract both sides with 4x squared. So minus 4x squared there and minus 4x squared there, right? So now we go to 0 equals, and then 50.5 x squared minus 4x squared gets us 46.5 x squared. And then everything else stays the same. 151 minus 151.5x plus 101.0. Well, this is great, right? This is great. Using math, which is why we call this part the math part, right? The math part. We were able to get we were able to rearrange our equilibrium expression to the quadratic form that we need to solve with the quadratic equation, right? Because now we have a here, b here, and c there to plug into the quadratic equation. All right. What's the next step then? The next step is to plug it all into the quadratic equation to solve for x. The thing that you have to remember though is that, remember the quadratic equation right here has an x squared, has a plus and a minus there. So you'll come up with two answers, right? And once you get those two answers, you'll use your chemistry knowledge or chemistry, reasonable thinking skills to figure out which one is the right answer, okay? And I'll show you how to do that in a second once we get those answers, okay? So knowing that the quadratic equation is right here, I would go ahead and write out both of them, especially since you'll be using calculators that don't allow you to solve for quadratics just simply. Okay, so let's go ahead and write them all out. So I'll do the first one here, I'll have to call x1, right? And that equals minus 151.5. Why do I do the minus? Because remember that the equation has a minus b right there, and then we already have a minus in the equilibrium, not the equilibrium, but in the quadratic equation there, right? In this form of the equilibrium expression for the quadratic equation there. So that's why it's minus, right? And so for this one, I would go plus the square root of minus 151.5. Again, I'm going to put my minus 151 or negative 151.5 into parentheses so that my square knows to do both those things, right? If you don't do this, your calculator will think that you're going to square the 151.5 first and then put a negative on it, and that would be incorrect because you have to square both the number and the sign, right? And that way the number turns out to be positive in the end, not negative, right? So you'll get the wrong answer if you don't put the parentheses around the negative sign and the number so that you can do a square, all right? I know calculators, they should be smarter than that, but they're not, all right? And then we'll keep on going. 4 minus 4 times 46.5 times 101.5. All right. All this is divided by 2 times A, which is 46.5. So if I were you and I were putting this into my calculator, I would do it one part at a time and write down the numbers as I go, just so I don't make any mistakes. You're bound to make more mistakes if you put the whole thing in the calculator and try to figure it out all at once, right? So the first thing I would try to do is multiply this part out first. The 4 times 46 times 101.5. Sorry, not 101.5, it's 101.0. There we go, 101.0, right? After you do that, then I would then do the square of negative 151.5. And then I would subtract them from each other, and then I would take the square root. Do it step by step, one term at a time, okay? And then I would add them to the negative, the minus negative, the negative 151.5, right? And then divide all that by 2 times 46.5. So I would do it all step by step, 2 terms at a time, right? Or 1 term at a time, but 2 numbers at a time, okay? That way you minimize the chance of you typing in something wrong in the calculator when you have too many terms in there at once. All right, then x2 will be equal to net minus, messed up my parentheses there. That doesn't look good. I'm going to fix that. There we go. Minus negative mean the same thing. 151.5 minus, that's a lot of minus signs. The square root, right? The square root of negative 151.5 squared minus 4 times 46.5 times 101.0. Okay. Then all of that is divided by 2 times 46.5. Okay. Good. Now we have those equations written out. We just have to put them into our calculator and then do things one at a time so that we don't get confused or mistype something by putting the entire thing into our calculator at once, right? And then that also saves on you having to make sure that you have the right parentheses everywhere, because calculators are stupid, right? All right, so if you go through and solve for x now, the first x you get will be x equals 2.323, right? And then the second one you'll get is x equals 0.935, right? And so once you solve for x, using the quadratic equation, that's what ends the math part, okay? So now we've ended the math part, okay, of solving this equation or solving this problem. Well, now we got to switch back to chemistry, okay? Using the chemistry is how we figure out which one is the correct answer. Is it the which one is the correct x? Is it the 2.32 or is it the 0.935? Well, let's go back to our problem, the chemistry side of our problem, right? And in the chemistry side of our problem, we see that our initial concentrations were 1 and 2, right? Huh. If we look at our x's, we have one that is bigger than both of our initial concentrations, which is impossible. You can't get an equilibrium concentration that is bigger than the actual initial starting concentration of any of the reactants, right? So just from that alone, we know then that that's the incorrect x. And the x that you should be using in the problem, right, is this one, okay? And it makes sense too, right? Because if you were to put the 2.3, what was it again? 2.323, right? And plug it in for x right here, and right here, you'd end up with negative numbers, right? For your equilibrium equation, equilibrium concentrations, which is impossible. That can't happen, right? They have to be positive. And so the only way that can happen is if you use this number, the 0.935, right? Great. So now we know what our x is, right? So back to the chemistry part, sorry. So back to the chemistry part, all right? We know that the equilibrium concentration for H2, let's do H2 first, equals 1.0 minus x. So that's going to be 1.0 minus 0.935. Oh, I lost something there. There it goes. And then we know that the equilibrium concentration for I2 is 2.0 minus 0.935. And then we know that the equilibrium concentration for HI, oh, I didn't mean to zoom in there, sorry. For HI is 2 times 0.935, right? And again, where did I get all these things? I got them from the last row of the ice table, right? Here's the equilibrium concentration for H2, 1 minus x. So here's 1 minus the x from the math part of the problem. Here's I2, 2 minus x for the math part of the problem. And then for the equilibrium concentration for HI, it's just essentially 2x. So 2 times the x from the math part of the equation, right? The math part of the problem, right? And so now all we have to do is do our simple math, right? And so I'm going to go ahead and figure this out right now. 1.0 minus 0.935, and that gives us 0.065, and that's our concentration for H2. So don't forget your M for molar, right? We'll do the same thing again, except this time it's going to be for I2, which is going to be 1.065 molar. And then we'll do 2 times 0.935 for the concentration of HI, which equals 1.87 molar. And that's it. And that's how we solve for this problem. So if you have any other questions, let me know.